Okay, so yesterday we did not do this problem because I didn't think we'd have time to treat it properly. We're going to try this using two methods. So just take a moment and draw y equals rad x. I suggest you make this the 0.11 right here. So we'll just make this 1, 2, 1, 2. Go ahead and draw the rad x curve. Something like that. Okay, and then we want to also draw the y equals x line. Like that. And you can see the bound region here is the red. Right there. Okay. And our goal is to rotate it around the y-axis. So let's get rid of some of the clutter here. If we're rotating around the y-axis, we should draw a loop-de-doo. Do you guys remember what a loop-de-doo is?
Yes.
Okay, hopefully. You don't want to forget the very scientific word, a loop-de-doo, like that. Okay, so loop-de-doo. Draw as many as you want. I'm going to draw at least one for the top there. So we end up with this interesting solid. From the outside, it just looks like a funnel. But if you look inside, it is not quite a funnel. It looks like one of those things you put your coin in at the mall, and it goes spinning around. It's got like a vortex kind of look inside. You put a coin in it, it spins around in a circle, and then it accelerates and goes faster and faster and faster and faster, and then it disappears, and you say, hey, where's my money?
It's generally the pyramid.
Okay? You guys seen those before at the mall? You put your coin in it?
Yeah, it's sort of like,
They steal your money. Yes, they're for charity though. It's a good cause.
yeah, steal your money. Steal your money.
Lose your money there. That's a good place to lose money. Okay. So obviously this is kind of the solid. It's not that hard to visualize really. But how would you find the volume? Well, it all depends on how you slice it. Okay? So you want to slice it into shapes you understand. Right? So if you were to make this thing out of Play-Doh, right, and then take a knife to it straight down, you'd find some very strange looking cross section. Something you don't know how to study maybe. But on the other hand, if you cut it straight across, you're going to get circular cross sections. You understand? So we're going to choose to slice it horizontally. So here comes the plane that's going to cut it in half. So we're going to slice it this way, you see. And the cross section in that plane will be, it's not quite a circle, it's going to have a hole in the middle. You see? Most of the cuts you make have a hole in the middle. The only exception I can think of is if you cut right at the very, very bottom, you might not have a hole. But all the other spots have a nice hole right in the center. Reminds me of a song. It goes like this. I ran around the corner and I ran around the block. And I ran right into a bakery shop. And I got myself a donut right off the grease. And I handed the lady a 5-cent piece. She looked at the nickel, she looked at me. She said, kind sir, you can plainly see there's a hole in the nickel and it goes right through. And I said, there's a hole in my donut too. Thanks for the donut. So long. All right.
That doesn't win a Grammy after
That's one of the most valuable things I've ever learned. Okay. Okay, so this is not quite a donut, it's a washer. If you give it a little bit of thickness, looks like this. But the area of it's simple. The surface, the top area here, the base area. That base area, we'll call it capital B, is simply pi big R squared minus pi little r squared, or you could just leave the pi outside. you don't like pi, you can leave it out there. Notice that the donut has a pi in it. That's very strange. Okay, so you got the pi outside there. That's the area. And if you want to think of it as a volume, like actually have some thickness, you have to ask yourself, does it have a thickness delta x or a thickness delta y? So look at the way we've sliced. Yeah, this would be its thickness if you drew it right on the solid. So you can see how that thickness is a vertical thickness. So I'm going to use delta y, multiply by delta y. Okay, so the volume is pi r squared minus r squared delta y. That's just base area times height. And in differential form, dv equals pi r squared minus r squared dy. Very good. Now, this is the tricky part, getting the radius figured out. Okay, so when you draw the radii, it turns out both of them are horizontal. Okay? So I'm going to try to draw my sample washer on my solid there. And you'll notice that the inner radius, little r, depends on the inner curve. That's the rad x curve. So little r is just, let me draw little r for you. Maybe I can enlarge this a bit so you can see it. Here's what's going on. You've got your washer here, like that. And this is your inner radius. It's centered right on the y-axis. So this side of it is x equals 0, and this side of it is x equals something, and it's connected to this curve, you see. So since this is the y equals rad x curve, another way of thinking of that is x equals y squared curve. You can think of this as the x equals y squared curve. So the left side of it is x equals 0, the right side of it is x equals y squared. Okay, so how long is the small radius? It goes from x equals 0 to x equals y squared. How long is it?
Y squared.
Y squared. Right. So the length is from 0 to y squared, so obviously the delta x there is y squared. So that's actually your lower case r. That's the smaller radius in this image. All right? So I would say that r, I'll use red to color code everything, r is y squared. Let's look at the larger version of radius. Okay, so I just drew the blue radius there. That goes between x equals 0 and the line y equals x, also known as line x equals y. So it's a little hard to visualize, but the radius runs from the axis of rotation to the outer point of the washer, namely from 0 to the curve y equals x, well, you can say x equals y. So how long is it from x equals 0 to x equals y? Simply y, right? Okay, that's one of the tougher steps, is figuring that out. But now we have our differential. Here it is. dv equals pi times, and capital R is just simply y. So I'll color code these. And lowercase r is y squared, so this is going to be a y to the fourth right here. So that says y to the fourth. I'll rewrite it here. Okay, that is by far the hardest part of the problem. The rest is simple. You're going to integrate both sides and give some meaningful limitations for y. Okay? So let's go ahead and integrate. Put an integral here to here. The left side is volume, of course. Here's your integral. Let's give some meaningful constraints for y. Look at your picture. Just look at the original image you drew. What's the least and greatest amounts of y in this picture? Everything fits between 0 and 1, right? And washers between 0 and 1. So that would be from y equals 0 to y equals 1 when you integrate. And the answer to this is right there on the page, isn't it? What does it say? What is it? 2 pi over 15. Yeah, so if you want to work it out, you can. It's 1/3 y cubed minus 1/5 y to the 5th. And when you plug in 1, you get 2/15 pi. That's the answer. 2/15 pi. So I'm kind of stopping before integrating because it really is just a polynomial. Okay, so we don't even have a name for that shape. You know what I mean? But we can kind of solve it. That's kind of cool. I think we should dub it. We should give it a name. What should we give it?
Shores cone.
Shores cone? Point stealer?
Shores point.
The charity cone? Make up a name. Okay, so we're going to redo the same problem, only this time we're going to take a completely different approach. Okay? So let's try it again. All right, same drawing. We'll draw a little bit bigger this time. This time I'm going to make my y equals x line, and I'm going to call this point 1, 1. Just a little too small last time to see. And here's my rad x curve. Like that. And the loop-de-doo is the same. We're actually still rotating around the y-axis. The solid looks the same. So there's your solid. Okay, now we're going to take a completely different approach. This time we're going to try to use cylindrical shells to model the same thing. For example, one shell might be right here. Okay? Another one might be this green one here. This is just slightly outside it. It has a slightly different height, okay, than the red one, and a slightly different radius from the red one. But they're so close. That's the intention anyway. Now imagine if you took this shell, the red-green shell, and you did another one just slightly to the outside of it. So one shell with a slight bit of thickness, right? Another shell with a slight bit of thickness around that. Another one. I want to grab one of the posters on this concept of stacking surface areas together to form your solid. You would actually be working radially, so your first one would be very, very small, and it would actually be way down here at the bottom.
So are they stacking on top of each other?
No, they're stacking around each other, like this.
Or wouldn't it make it too big for the...
As we create these shells, we need to keep in mind that we don't want any of them to lie outside the region. So we don't want any of them to protrude through the black curves. They all have to have their heights bound to the curves, okay? And we need their radius accordingly. So you kind of draw the height first. That's why when I drew this, I'll redraw, but when I drew this, you should practice drawing. This is kind of hard to learn. The first shell I drew was right here, and I just went straight up and down first, except my drawing looks bad now. Let me fix my curve here. All right, so the first thing I did was I drew right here. I got the height bound between the two curves like that, and then I wrapped the lateral surface onto it like that. So there's the shell, and it has a differential volume, so you really don't have to draw two of them, you can just draw one. But we already worked this out earlier that volume of that thing is 2 pi r h dr. Okay? So we went through kind of a rigorous opening thing, warm-up type thing this afternoon. That's what we came up with. So we believe that that volume, that little shell is like a 2 pi r h surface with a slight bit of dr thickness. Okay? And if you laid it completely flat on a table, so here it is being laid flat on a table. Okay, laying it flat. This is the surface sort of cut open and laid flat on the table. We believe it would have length 2 pi r and width h and thickness dr. So it's like a rectangular solid almost. Length times width times height is 2 pi r h dr. Okay, question?
I still don't understand. So if you're making, so you have dr and it's going to be increasing eventually, right? Although they're really small.
dr won't increase, but
Well, dr will.
you
but
mean r?
R will increase.
Mhm.
How does it not exceed, like, when it takes up the full shores cone, I guess, how does it not, like, go out of it? Or it's getting wider and...
Yeah. Well, we have to adjust the height accordingly. So let's say you want to draw a bigger shell, or a shell with a larger radius, you might be sacrificing some height. For example, one of the shells has a huge radius, but look how it's confined vertically.
So it does stack on top of each other.
They're nested inward to outward, but yet these ones are being built upward a bit. On different solids, they would truly look like one was inside the other. So for example, if your solid was a little bit simpler, for example, if there was no y equals x line, if you were just rotating this around, for example, you would get a true funnel, you see, with no hole in the middle at all. It's actually a solid, like a Hershey's Kiss, upside down. And what you would do is you would draw the shells. Actually, this isn't a very good example. Let me draw another one to answer your question. Let's say your curve looked like this. Okay, and you rotated this around the y-axis. It would look like this. This would be like a Hershey's Kiss, and there would not be any hole in it, because I don't have two curves. And then when you draw a shell, the one with a small radius would look like this. One with a slightly larger radius would look like this. Notice it's a little bit shorter. See?
So
The
it
next
moves-
one,
so
go ahead.
it moves up, kind of. It moves along the curve to make the cylinder.
Yeah, the heights are bound to the curve. The radii are just slightly larger than the previous one. It's very hard to visualize, but this one, the heights are diminishing as the radius goes out. On this one, both height and radius are kind of changing as you draw the shells. If I gave you some cardboard, and I asked you to build a short cone, one of the ways you could do it is by forming tubes. You could just form a bunch of tubes and get this big cylinder, and then you could shave off the outsides to make it look like a cone. Or you could just construct them right the first time. You could just build all these cylindrical shells, all the right heights, and then just kind of glue them together and form this solid. But you have to keep this edge straight and this edge curved inside. Okay. All right, but the goal is to just understand that surface area does contribute to volume in this radial sense, and then you can just integrate. So now the tricky part is going to be trying to figure out what R is and what H is. Okay? So let's go back to our drawing board here. Let's just look at the red shell only, because you only need one shell to understand the whole ordeal. Okay, so here is our shell of choice. The radius, notice which direction I just drew that. Which direction did I just draw that? To the right. So I could just call this length x. Isn't that true? Okay, so for my radius, I'm just going to use just plain x. What am I going to use for h? H is a little more complicated. H is right here, you see. It's the length between this point and this point. Now, I guess I could put delta y, but I don't want too many variables here. I've got an x already. Why not treat this point as a y value of rad x, and this point as a y value of x? So I'll write that down. But the topmost point here is at y equals rad x, and the bottommost point is at y equals x. So the length between them, this black segment, is literally rad x minus x. That's how long it is. Okay, so here's our differential in one variable. It's 2 pi x times, and then we're going to put in rad x minus x. There you have it. In fact, what is my change in radius? As you increase the radius, what's dr? Which direction is it? It's an x direction change, right? So the thickness of the shell is also a dx. So I'm going to go ahead and replace this with dx. Dr is dx. If you don't believe me, just imagine which direction these shells are actually growing in, right? Every time you increase the radius a little, you're increasing the x a little. Okay, and therefore we can replace that with dx. So here it is, finally, truly one variable. I'm going to go ahead and distribute this. That's x to the 3/2 minus x squared. And now we'll just integrate. Okay, integrating the left side, we get v. Integrating the right side, what are some meaningful constraints on my x? Well, don't think too hard on this. I've been guilty of thinking way too hard about my limits of integration. What's the smallest x value in my original plot? And what's the largest x value in my original plot? So remember what we started with in this was we started with this bound area. That's all that we had originally on this picture. This is our starting image before rotation. What is the smallest x on this picture? 0, right? What's the largest x on this picture? 1. That's it. That's the limits of integration. So I've definitely been guilty of overthinking those. Just go back to your original bound area, whatever the domain is, that's your limits of integration. Done. This also gives us, of course, 2 pi over 15. Question?
I think in your final integration.
I wrote 3/5 there. What's that doing there? I meant to write 3/2. Is that what you're going to say? Thank you. All right, this also comes out to 2 pi over 15, like we said. Shouldn't be any different. We just constructed it a different way. So you might say, Mr. Shore, I would never use that method. It's the lamest thing I've ever seen in my life. Maybe you think it's lame, but it's really good to have more than one perspective on a math problem. And as we'll see after the AP test, there are many perspectives for finding the volume. We could actually do this using 2 integrals, okay, called the double integral, or even a triple integral. You can solve problems more than one way. We know that, right? The other reason it's healthy is because sometimes you might try to use washers and it doesn't really work. And you realize this method isn't working at all. I'm stuck. So let's look at example 7. We're going to skip over example 6, and I'll show you what I mean. So skip over 6 and go down to this. And you really don't need this piece of graph paper here. I don't know what that's doing there. Go away. There we go. And the other thing is, we're going to be revolving this around the line y equals 3, which is technically not even shown. So we're going to have to extend our y-axis a bit. So everybody extend your y-axis. Give it some length, because you're going to be rotating this thing around vertically. Y equals 3 would probably be right about here. This is our axis of rotation, unfortunately. So this happens sometimes. Your axis of rotation takes you right off the page.
Is that what the graphic was for? So we can draw this?
Maybe. You could try drawing it over there if you like. Or you could just, is there a backside of that page? Can you,
This is the back of it.
that's the back? Okay. Maybe you can just do this one on a separate piece of paper too if you wanted. So what's going to happen is this solid is going to come up and out of the board, okay? Like this. It's going to come out at you, and then it's going to wrap up back into the board, behind the board, and back around up against the board again. So it's going to come out like this and form this solid in space. Very hard to visualize, and I can't really animate it, but we can draw loop-de-doos. Let's draw a couple loop-de-doos to help us visualize it. Make my line straighter. So we're going around this way. And if you took AB calculus last year, you did not learn the shells method. So this is brand new. It's just a different DV that you're integrating. All right. So here's a couple sample loop-de-doos. Here's one loop-de-doo for that point. Notice that the radius is the distance between y equals 3 and the point 2, 2. In other words, the radius is 1. Here's another loop-de-doo over here. Oops, I was going to do loop-de-doos in blue. So this loop-de-doo is going to be like this. And this loop-de-doo is going to be the biggest one of all. This point is going to rotate all the way up to y equals 6. So it's going to look something like this. It's not quite a bundt cake. It looks almost like a... Yeah, I guess it could be like a bundt cake.
I know, like one of those lava cakes.
It's an interesting solid. Something like that. Okay, so it's supposed to look 3D. Okay, it's supposed to look 3D, and this is probably more curved here. Let me fix it a bit if I can. A good sketch goes a long way when you start drawing the shells and stuff, so take your time with it. Something more like that. Okay. So if you read the instructions to this problem, it says, why is it that washers is a bad method and shells is a good method? So we're going to find that out. So let's say you started doing this problem by using a washers method. So you slice it vertically like this. Okay, you slice it like that. Fine. The problem is you're supposed to find the radii here. Big R and little r. And the problem with that is you'll notice that these radii are drawn vertically. See that? So like this first radius goes from here to here. Second radius goes from here to here. Or you can draw them going upwards, doesn't matter. The point is, how are you going to find the y coordinates of the endpoints of the radius? I don't think that's going to happen. We can say that the top, let's say we draw a radius coming straight down like this. Okay, that's our little r. The top of this is at y equals 3, for sure. But where's the bottom of it? On this curve. Okay. What's the y coordinate? If you look at the way this curve is defined, it says x equals y to the fourth over 4, y to the fourth over 4, minus y squared over 2. How are you going to get y? How are you going to isolate y so that you can get that bottom point? You can't do it. I mean, you can, but you have to use like quadratic formula. It's horrible. So it just doesn't look like you're going to be able to get the y coordinate at that point very easily. And if you can't get that, you won't know what the radius is. If you know what the radius is, you can't set up the differential. So this is just a dead end, you see. Does everyone Everyone see what happened there? I can't isolate y, so I can't get my radius figured out. Tough noogies. So, we're going to have to try the shells method. Okay? So what does the shells method entail? It entails drawing shells, not washers. All right, so let's try that again. 3, 4, 5, 6. We have a point there, and a point here, or here. We're rotating around this line. I don't even claim to be an artist. Let's try it again. This time we're doing a totally different approach. How about a shell? So remember how the shells work. First you draw a segment that connects the two curves. And then you draw the shell in like that. So this is a shell. It's actually horizontal. One thing you need to know about shells is the axis of the cylindrical shell is the axis of rotation. So if you're like, where's the shell? Just imagine the axis that runs through the center of the shell is also your axis of rotation. So that'll help you find it, okay? All right, let's study the shell. So the shell has differential volume 2 pi r h dr. Let's try to make sense of this. We'd like it to all be in one variable. Okay? Let's study the radius first. So the radius, if I were you, I would draw it coming straight down. Like that. Question?
For the shell method, how does like the cylinder account for like the hole in the middle of the?
Well, the cool thing about these shells is you only have to build the shells that fit in the shape. So, for example, another shell I might construct is this one. See? And another shell might be this one. I don't plan on building any shells in that empty space in here. I want that hole in the middle like a sigma arm. So I'm never going to build any shells with a radius less than 1. All my shells will have a radius of at least 1. See? Because you're trying to imagine constructing a solid, right? So if you were building this using, if I gave you a bunch of like sheet cardboard and you were forming tubes, you would never build anything smaller than radius 1 because there is no such shell. All the shells are at least radius 1 all the way up to radius 3. You see? Okay. So now let's go ahead and write down that radius. Which direction did I draw the radius? Horizontally or vertically? Vertically. So one way to think of this is up here at y equals 3, and this is down here at just some random point xy. I don't know what y value, just some y value. So I could think of this length as 3 minus y. Now the only time that could get me is if, for some reason, I need to put x's in here. I might need to put in an x or something there, but I might not need to. Let's see what happens next. I can always come back and substitute something in for x, right? Let's look now at the height. The height of the shell is this green segment here. The y coordinate at this point is 3, you agree? And the bottom of it is at some distance off the x-axis, right? It's just some arbitrary distance above the x-axis. I'm going to call that y. I might need to substitute in, like square root of 2x or something later, but if I don't need to, then I certainly will not. Okay, so I'm going to leave that as 3 minus y for now. And then my horizontal segment there, that's a delta x. You can see, this is perfect. They told me that this point on the right is x equals y squared over 2. And they told me that this point on the left is x equals y to the 4th over 4 minus y squared over 2. So here's your green segment. I'll draw it over here. This is at x equals y squared over 2. And this is at x equals y to the 4th over 4 minus y squared over 2. So how long is the segment? It's just the difference. Find the difference. So what's y squared over 2? Minus y to the 4th over 4 minus y squared over 2. Looks like you got a 1/2 y squared plus a 1/2 y squared there. Okay, so I'm going to decide here what this is. This right here, I just subtracted. It comes out to y squared minus y to the 4th over 4. It's just the difference in the two equations they gave me. They gave me an f of y and a g of y, and I just subtracted them. I just subtracted the endpoints there to get that. All right, so my shell height, I drew it over here because it's a little bit hard to fit it into the picture. There it is, this minus that. Okay, and now let's talk about dr. So we figured out what r is, we figured out what h is, let's talk about dr. So if you were to increase the radius of this shell just a hair, which dimension are you moving into? The x or the y dimension? That's a slight change in y or x. Slight change in y. So this is dy. dy and dr are the same thing. All right, so here is your differential. We're ready to go. dv equals 2 pi, I need a little more space, I'll write it at the bottom. dv is 2 pi r h, oops, it's in my, I drew it up here in my picture. Just erased it all too. Man, that stinks. R was 3 minus y. H was y squared. Thank you. Y squared minus y, 1/4 y to the 4th. Basically, that's my h. Okay, I was just constructing this when I accidentally erased it. Y squared minus 1/4 y to the 4th. And we decided that our dr really represents dy for this problem. And then you'd integrate both sides to get your answer. Okay? So what would be your meaningful constraint on y here? Remember, you just look at the original bound area, so don't get carried away. Just look at your original bound area. What's the smallest y in this nifty little blue region? What's the smallest y value? 0. What's the largest y value? 2. Yeah, don't overthink it. Just 0 and 2. So we're going to be integrating from 0 to 2. And that's an ugly looking integrand, but it's just polynomial stuff. You can FOIL it if you want. It's just 3y squared minus 3/4 y to the 4th minus y cubed plus 1/4 y to the 5th. I'll try to write it all out for you. So it's 3y squared minus 3/4 y to the 4th minus y cubed plus 1/4 y to the 5th dy. And to differentiate, plug in the numbers. It's just 2 and 0. And what did I give you for a final answer? What is it? 56 pi over 15. Okay, so do me a favor tonight. See if you can write the reason I switched methods midway through this problem. Why did the Washington method fail me? Why did I switch to the Shell's method? It has something to do with I couldn't isolate something. You see that? Yeah, I was having trouble writing my expressions. It wasn't very good. And you can also try example 6 on your own if you want. I only skipped it because it's not necessary.